Hi, y'all, and welcome to Professor Truelove's Concepts for Nurses series. And in today's episodes, we will be covering EKG or ECG basics. That is, the basics of electrocardiogram. We are still using as our sources Iggy's Medical Surgical Nursing, 9th edition, and Soul's Introduction to Critical Care Nursing. Let's review some electronic facts about the ECG. It is a graphic record. It detects the magnitude of the cardiac electrical activity. Plus, it detects the direction of that cardiac electrical activity, and it records it over time. The ECG can be viewed both on a monitor, a TV or computer monitor, but also on ECG paper, a specialized ribbon of paper. This records the ECG. It uses grids to permit measurement of time, that is, left to right, and the same grid measures amplitude, up and down, as well as direction, up and down. Amplitude is the amount of energy being detected, and direction is how the energy travels in the body. Again, normally the SA node is towards the upper right of the body, and so we would expect the energy to travel from upper right to lower left. The ECG paper does measure amplitude, and it's divided into big squares and little squares. You will see on top that one small square equals 0.1 millivolt up and down. However, left to right, one small square equals 0.04 of 1 second, or 400ths of a second. One large square equals 0.5 millivolts, or 0.2 seconds of time. Also look up a little bit to your left. Now you see that because one large square equals 0.5 millivolts, well, two large squares is going to equal 1 millivolt. And if we add 5 squares together, 0.2 equals 1. So 5 large squares will equal 1 second. You might ask yourself, how do these parts correspond to what's going on in the heart? How does this graph represent what's going on in the heart? Well, as the SA node generates an impulse and atrial excitation begins, this is represented in the beginning or the upslope of the P wave. Now, that impulse goes through the atria where it completely depolarizes the atria. This is the P wave. And as that impulse is delayed at the AV node, there is a little pause called the PR interval. At that point, the impulses passes through the heart apex. Ventricular excitation begins, and we see that at the very beginning of the Q wave. As ventricular excitation is complete and the impulses go all the way to Purkinje's fibers, we see that the QRS complex, which represents complete ventricular depolarization, has been complete. So here's another view of that exact same mechanism. Here we see as the P wave begins, the SA node has fired and energy is traveling down the pathways and in through the atria. As the impulse completely permeates the entire atria, we see the P wave is complete. Then, this is the beginning of the depolarization of the ventricles. We see the energy starting to run through the upper part of the ventricles, represented by the QRS complex. At the end, we see repolarization, and that's represented by the T wave. So if you're looking at this graph, it goes left to right, where yellow represents depolarization and green represents repolarization. So normally, all of that energy traveling from the SA node through the internodal pathways, through the AV node, down the bundles, into Purkinje's fibers, into the ventricles, is represented by a graph that looks very similar to this, where we see these different deflections from the flat line. By the way, that's called the isoelectric line. These different deflections, upward and downward, are known as waves, and they have their own names, and they represent different parts of the electrical activity of the heart. And these deflections are known as the waves of the ECG. And we've called them P, Q, R, S, and T waves. And sometimes there's even a U wave, and then even an F wave, and sometimes a flutter wave. You'll see what I mean. In a positive lead, going from left to right, the first smaller upward deflection is known as the P wave. The P wave represents atrial depolarization. You should consider the waves of an ECG to start when the deflection leaves the isoelectric flat line and goes either up or down. And then that same wave comes back down to, or back up to the isoelectric line. Here, notice the shaded area. It is the entire up part of the wave and the downward part. That is the P wave. Just to the right of the end of the P wave is a flat area that is isoelectric. This is known as the PR segment, and the area from the beginning of the P wave until the beginning of the Q wave, that is in this picture, the beginning of the shaded area all the way through the hill to the flat line until it starts to deflect downward, that whole area is known as the PR interval. So recall that the P wave represents atrial depolarization, and the PR segment represents that impulse being held up a little bit, slowed down by the AV node. The next part is a complex. It's actually a series of three waves. The Q wave, shown here in a small downward deflection, and the R wave, shown here in a positive lead, shaded. Now, notice very carefully that the shading doesn't start until the wave deflection passes through where the isoelectric line would be, and that the R wave is not just the upward deflection, but it is the upward and downward deflection. The R wave is followed by the S wave, seen here as a downward deflection. These three waves are all clumped together and called the QRS complex. They represent ventricular depolarization, and it is measured at the beginning of the Q wave. Now, if there's no Q wave, you measure it from the beginning of the R wave, and it goes all the way to the end of the S wave. Now, where the S wave stops going up and suddenly goes flat again, that actually has a name too. That's called the J point, and it represents the junction where the QRS complex ends and the ST segment begins. After the J point, there is another flat isoelectric line. This is known as the ST segment, and it represents early ventricular repolarization. This is also an area that may change for a person who has coronary artery disease and conditions such as myocardial ischemia or myocardial infarction. The end of the ST segment is where the T wave begins, and that represents ventricular repolarization. Now, the interval, or the amount of time from the beginning of the Q wave until the end of the T wave, actually has its own name. This is called the QT interval, or QTI. And you should know that it represents the total time required for ventricular depolarization and repolarization. Taken all together, we should have a series of waves that is a set pattern of a healthy heart that we call sinus rhythm. Again, represented here as the P wave, the QRS complex, and the T wave. Notice on this picture, the flat line is called the isoelectric line. There is no positive or negative charge on that line in relation to what the body is already doing. Occasionally, you may see a little extra bump after the T wave. That's called the U wave, and it represents late ventricular repolarization. And U waves can either be pathological or non-pathological. That means they could represent something like an old myocardial infarction, or they could just be a benign sign of a heart that is repolarizing a little bit late. However, sometimes things don't work out as well as we would have hoped, and there's some irregularities in the heart. Sometimes the heart, or the heart chambers, I should say, beat very, very quickly. And if it happens in the atria, we call this atrial flutter. Atrial flutter, when we look at it on an ECG, has a very characteristic pattern that remind a lot of people of the teeth of a saw or triangles. For that reason, they can be called delta waves, flutter waves, or even F waves. And here we have an example of atrial flutter. Notice that there are 3 triangle-shaped waves for every larger QRS complex. We would say, therefore, that in this case, we had atrial flutter in a 3-to-1 ratio. One way to imagine atrial flutter is to imagine the wings of a small bird flapping rapidly. However, there's yet another pattern that can be picked up on our ECG, and it is when the muscles of the heart, instead of moving with organization, move chaotically. Instead of having a pattern that squeezes and relaxes, the muscle simply quivers. If the muscle's quivering, we call that fibrillation. And we see on the ECG something called fibrillation waves. This indicates that the cardiac muscles are firing chaotically and without organization, and it can be found in both atrial fibrillation and ventricular fibrillation. Now that you have started to understand how we identify the different waveforms, another important tool to have when interpreting ECG is, what is the rate of this heart? How fast are the atria and ventricles actually firing? Well, we're going to use the different distances of the ECG pattern. We may measure it from one P wave to another P wave, demonstrated here as the P to P interval, or we might use the distance between one R wave and the next R wave, known as the R to R interval. In both cases, that'll help us to measure how fast the heart is beating in beats per minute. We'll detail 3 different ways to measure heart rate on an ECG. The first way to measure heart rate is to count the number of R waves, that is, or QRS complexes, in a 6-second strip. Then multiply that number by 10. How will you know how much time has passed for 6 seconds? There's a couple ways to do it. An easy way is simply to count the large boxes. Count up to 30. Remember that each of these large boxes equals 0.2 seconds. So 5 of these boxes equal 1 second. 30 divided by 5 equals 6. Therefore, that means 30 large boxes equals 6 seconds. Once you've mapped this out, you simply have to count the number of R waves to determine an approximate rate. In this case that we're looking at, you see 7 R waves, so the heart rate on this EKG would be approximately 70 beats per minute. A second way to determine rate is to use the small boxes of the graph paper. You count the number of small boxes for a typical R to R interval. Divide this number into 1500 to determine the heart rate. So in this image, the number of small boxes for the R to R interval is 22.5. To determine the heart rate, divide 1500 by 21.5, which is 69.8, or approximately 70 beats per minute. This is, by the way, the most accurate way to determine rate. In the case that the heart rate is irregular, the rule is to take the longest possible R to R interval and determine that rate. Then find the shortest possible R to R interval and determine that rate. Add those two numbers together, divide by 2, and this will be your average heart rate. The third way to determine heart rate is called the 30, 150, 100 method. Each large box represents a diminishing rate. So you pick an R wave that occurs on or very near the border of one of the large boxes. Use that as a starting box. Then label each subsequent large box as the following heart rate: 300, 150, 100, 75, 60, and 50, as you see in this picture. For this method, simply count the number of large boxes between one R and the next R. In this strip, from the start here, notice that the next R wave occurs between the 75 and 60 marks. Therefore, you would determine that the heart rate for this strip is approximately 70 beats per minute. And now that you have the basic guidelines, this will make it easier to actually start to interpret the EKG. And yes, that is the end of this podcast. However, on our next podcast, we will start to dissect the different parts of the EKG. So I hope you were able to learn a little bit with this podcast. This is Professor Truelove, and I hope you come back for more. And if so, I'll see you then.